hit record. So now we're done. Okay. So we started talking about linear regression. And one of the things that we had said about coefficient estimates we see. So remember, how do we interpret these? It was a 1 unit increase in X causes our Y variable to increase by whatever that slope coefficient is. Just any linear line, that would be how you interpret the slope. All of our slope coefficient is the slope value. Now, we also had a standard error. We said, if I take an infinite number of samples, I'm going to see slightly different slope coefficients because it's going to be a slightly different number or group of people. Now, what will end up being true is I have a distribution to these slope coefficients that I see. And we said it's going to look like just like a sample mean distribution. So if I took an infinite number of samples, run these regressions, I'll end up seeing, as long as I have a sample size over 30, that my slope coefficients, you can almost, I don't usually say it this way, but you can think about your slope coefficient is always going to be a sample slope coefficient. Okay? So you would see kind of this distribution, and it will be centered around whatever that true slope coefficient is, if you had the population data. But just like any statistic, when we calculate a mean, it also has a standard deviation. Well, essentially, we call the standard deviation of our slope coefficient our standard error. So typically, I'll sometimes kind of write this as like that coefficient's standard error. Now, I had the equation on the slides, but the part that we're really concerned with is we've got what? We're minimizing kind of the sum of our squared error terms, right? So our error was just the difference between our actual Y values and our predicted Y values. What was here was kind of this n-2, and then there was something we really don't have to worry about down here, right? Because it isn't influenced by the sample size. So if I'm thinking about this fraction, just like if I had sample means, if I had a higher sample size, what's going to happen to this fraction in the numerator? The denominator is larger, the fraction goes down, right? If my numerator is smaller, what happens to kind of this standard error? This is a statistics class. If you guys don't know, if the numerator is smaller, what happens to the fraction? It's larger. The numerator is smaller, the fraction is lower, right? If I take a smaller number and divide it by the same thing, I'm going to have a lower value. So what's going to happen to my distribution? If the standard error essentially represents a standard deviation, or how spread out my distribution is, when it's lower, that means my distribution is more tightly centered, or we might say it's more peaked, right? So when my sample size is higher, I kind of get this more peaked distribution. Why is that good for me? If all I'm seeing is one sample coefficient, what is it now more likely my sample coefficient is close to? The probability of all the values near what the true coefficient is, all those probabilities have went up, right? Well, all the probabilities of values further from that true coefficient, if I had the population data, all those probabilities are lower. Right? So that's a good thing. I want to try to get as accurate of an idea of what that true effect is between X and Y, or that true relationship. Okay? So that's kind of one of the influences of kind of having a higher sample size, is it makes sure that we're more likely to get a slope coefficient that's close to that true population value, right? Now, we need that kind of central limit theorem, which is just that we need a sample size over 30, but that as that sample size gets larger and larger, our distribution is getting tighter and tighter around whatever that true value is. So same kind of a thing that applied to the sample means. Okay? So what about if we think about statistical significance? So I said last class, when we look at this regression output, we can do different types of tests, but for this class, we're always going to assume that that slope coefficient is what? So with the idea of hypothesis testing, I'm trying to test for something. So what do? I stack the deck against myself. I assume the opposite is true. So if I want to find an effect between X and Y, what do I assume is true? That there is no effect, or my slope coefficient is equal to 0. Now, later on in the semester, if you kind of took an additional statistic, you don't have to just test against 0. I can assume that coefficient is any value that I want. So this kind of gamma 0, we won't really use that a whole lot. because we're always, I said, going to start out assuming that that slope coefficient, there is no relationship or that it's equal to 0. And by saying it's equal to, what type of tailed test do we always have? Two-tailed test, right? So when we find this sample coefficient, how would we kind of find the kind of resulting p-value? So just to kind of do a review. I'm trying to go very slow through this. I probably should go a little bit faster, but I think we're on, it's not too bad. So here's my distribution, right? I know that as long as I have a high enough sample size, it should be kind of normally distributed. So whatever sample coefficient value I find, I can turn that into a standard normal distribution. Now, what Stata will do is technically we should be using the student t distribution, right? Because we only have sample data. However, anything over a sample size of 30, that student t is so close to a standard normal, the standard normal is a good approximation. So what would we typically do to calculate a test statistic? You would take the sample mean and subtract the assumed true mean. Well, for us, what's the statistic we're looking at? Not a sample mean, a sample coefficient. What is the assumed true value of that coefficient? I just said we're always going to assume it's equal to. Yeah, so technically I am subtracting the assumed true value, but if the assumed true value is 0, I can kind of ignore that, right? And then usually we would divide by the standard deviation of our sample mean. Well, now we have slope coefficients, not sample means. I said, what's the standard deviation of our slope coefficient? The name we use for that is the SE, or standard error, right? Or standard error of our slope coefficient. Okay. So it's the same idea, right? We're taking the sample statistic, subtracting the assumed true value. It's just the assumed true value is easy now, it's just 0. And we're dividing by the variance, or a scaled version of the variance of that sample statistic, okay? So once I turn this into a test statistic, what would I do? Well, technically, so this is my test stat. I could use that standard normal distribution, use the table, look this value up, find the probability I saw that or anything greater. However, if it's a two-tailed test, when I'm assuming that this is equal to 0, if I see something above that, it would have been equally as likely for me to see something below that. So I would take this area and then do what? Multiply it by 2, and that would give me my p-value. Or this interpretation of our p-value is essentially, what's the probability I saw the sample evidence I did that went against what I assumed to be true, or evidence that it would have went even more against that, right? Or would have been even more damning evidence. Sometimes I'll phrase it, okay? And so here, if I wanted to draw this out, I am finding this area, but technically I'm taking that, multiplying it by 2, because it would have been equally as likely for me to see sample evidence that went against that null on the other side, okay? So I might be jumping the gun a little bit here, but I know I've got this later on in the slides, and I think now is kind of a good time to do this, okay? So let's say we're going to kind of throw everything together here. Got my distribution. I don't know. Let's say my sample size is 50. I see sample coefficient of 5. I'm just choosing random numbers here. Well, I could convert that into a test statistic. All right. Find the area kind of, to the left, or sorry, to the right of that, multiply by 2 to get my p-value, okay? Let's say I found that same sample statistic, same slope coefficient, but I found it from a sample size of 100. Okay? Well, remember, here's my equation for that test statistic. And we had kind of behind the scenes what this standard error equation was. If it's helpful for you to think about this way, we're not going to get lost into the actual calculation. You can almost think about this standard error is essentially going to be the sum of those errors divided by n minus 2. There's more to it, but this kind of helps us get this concept down, which is that if I take a higher sample size, seeing that same slope coefficient, what's going to happen to this distribution? But we said the values further from that assumed true value of 0 will become less likely. Values closer to it are going to become more likely. So I get a much more peaked distribution. So seeing the same slope coefficient output from Stata, that same 5 for my slope coefficient, what's going to be true now about its standard error? Well, if I take a higher sample size, the denominator is larger here, what happens to this fraction? Smaller. This denominator now is smaller. What happens to my test statistic? Larger. So this same slope coefficient would now not be, call this like our test statistic for a sample size of 50. Notice now the area to the right of that value, much smaller. Now, when I convert that to my student t-distribution or use the standard normal to approximate it, it's going to give me a larger test statistic. So I might see a test statistic that's way out here, seeing the same value for that slope coefficient, but from a larger sample size. And that kind of makes sense. If I find the same evidence, but I found it from a larger number of observations, it should be more likely what I found is accurate. If I find it from 2 people, who the hell knows, right? But if I find it across 2,000, probably going to be pretty accurate. So what happens to that test statistic? It gets larger. What's going to then happen to my p-value? Well, if the distribution is more peaked, that area to the right should be smaller. So if my test statistic is larger, that area is going to go down. Now, when I multiply it by 2, I always multiply it by 2, so that shouldn't change the direction of it, it's smaller or larger. So higher sample sizes, the end result walking through all these things is that it makes it, if I have a smaller p-value, what ultimately is our rejection decision? We can compare 2 ways, right? We've got our critical value and our p-value approach. The easiest is going to be the p-value approach, right? So that p-value, right, we always reject if it is less than these kind of benchmark alphas. We said our benchmarks are like the 90, 95, 99% confidence levels. So if I've got my 90, 95, 99% confidence, what were the corresponding alpha values? So the way that I always think of alpha is what is the percent that would get me to 100 and then decimal form, right? Because alphas, we're looking at p-values, we're looking at probabilities, not percentages. So 90, my alpha would be 0.1, 0.5, 0.01. So if my p-value is getting smaller, is it going to be more or less likely I can reject the null? More. Yeah, if I only reject when this is true, when my p-value goes down, I'm more likely. And then if I had smaller sample sizes, everything would just get reversed. It's harder to reject the null. Also, what's another way I make my rejection decisions if I don't use the p-values? I can compare the absolute value of my test statistic and say if it's larger than these things that we called critical values. And we're always just kind of comparing them in absolute terms. Now, all a critical value was it was the z or t value that gave me those desired alphas, right? So we can kind of think about here. If I was to plot my critical values for the 90, 95, 99% levels, it would just be the value that gives me 0.1 total in the tail. So technically for a 2-tailed test, I have 2 critical values, right? 1 negative, 1 positive, because evidence on either side goes against the null. So this value, if we look it up, we use the standard normal to approximate it. This should always be, was this 1 point? It's not 2a. This is going to be 645 if I'm doing this from memory, correct? Okay. And then if I have my critical values that correspond to an area of 0.05 in the tail, or of that alpha, that was always going to be 1.96, a negative 1.96. And then if I want to look at 0.01, if I remember this correct, so that goes 1.96. Is this 2 point? I'm going to say it's 5.8. I can kind of check on the tables here in a second, or we can kind of check, but I believe it's 2.58 and negative 2.58. Okay. So whenever I see a test statistic, so this is always going to correspond, this z value will correspond to this area total in my tails. So if I ever see a test statistic that's right here, Well, if it's greater than my critical value, I should reject. But notice, if the area to the right of this critical value, or kind of the absolute terms, is 0.1, what does the area to the right of this test statistic have to be? Less than 0.1. What's the area to the right times 2 of my test statistic? That is my p-value. So my p-value will always be smaller than that alpha I'm comparing it to whenever my test statistic is greater than my critical value. It's almost like we're just kind of comparing things on 2 different axes, right? So this is kind of a summary of kind of what we're doing, right? Like I said, this should have been, hopefully the replacement lecturers went over some of this with sample means. We're now just putting it in the context of sample coefficients. Okay. Any questions on this? I'm just going to keep using this in building. So any questions at this point that you want to see clarified? Now's the time to ask. Okay. All right. So here's kind of my different steps when I'm running these hypothesis tests. I'll first figure out the null alternative. That's easy for us because I said we always assume the slope coefficient is 0. Right? We always know we have a two-tailed test. We don't have to worry about degrees of freedom. State is going to correctly identify what student t-distribution we should be using, so we don't even have to approximate it with a standard normal. Spectral line alpha level, this is generally in the types of questions I'm asking you. I'm always going to be using the same 3 benchmarks, right? That was the 0.1, 0.05, and 0.01 because it corresponds to 90, 95, 99% confidence. We will calculate our test statistic, then either compare our test statistic to the critical value, or we can use that test statistic to find a, let me see if I have it, a different slide here, so I didn't put it up here, but we already talked about it. I can use the test statistic to instead find a p-value and compare that p-value to alpha, right? Either way I can do that. Now we'll see once we start working with some state output, this stuff kind of is like behind the scenes and we kind of forget about it, but I think it'll, you know, it is floating around behind the scenes. So let's say, and I already wrote out this test statistic equation for you. We talked about the standard error. So let's look at some actual output. So maybe I want to know the relationship between number of days using marijuana and income. I think we used this example last class. So just to get some practice, how would I interpret this slope coefficient? For every one additional day of marijuana use, right? The expected income, I think this was like monthly wages, would go down by $253. How would I interpret my constant or the intercept coefficient? Those are two synonymous terms. Stata calls it a constant. Usually, if we're looking at like a textbook or the way that people talk about it, we generally say it's the intercept coefficient, but two names for the same thing. So how would I interpret that?
The estimated income of someone who doesn't smoke marijuana.
It's going to be our average Y value or the average income, right? For someone who has an X value equal to 0 or someone using marijuana 0 days a month here. Now, would I say that this is statistically significant and if at what levels? So what's the p-value here? So whenever we look at a slope coefficient or the intercept, it tells us the coefficient, tells us the standard error. So let's say I left this off on a quiz. How could you reproduce the test statistics? So if I'm looking up here, all my test statistic is, when I'm assuming the coefficient, slope coefficient is 0, it's simply going to be what? Coefficient estimate divided by my standard error. So 253 over 48, it's going to give me about -5. And then Stata will use that test statistic, look it up. Once again, doesn't have to approximate. It finds the correct student t-distribution, doesn't even use a standard normal to approximate, and gives me the corresponding p-value. So here, what levels could I say this is a statistically significant effect at? Is that p-value less than 0.1? So I can reject that the coefficient is 0 at the 90% level. Is it less than 0.05? Yes, so I can reject that there's no effect at the 5%. Is it less than 0.01? Yeah, a p-value of 0, I can reject at any level, right? So this is a very strong effect. Okay? Now, what I can also use are my confidence intervals, okay? So I think I'll kind of come back to this here in a second because I've got a slide for it. But notice, I just want to point that out. Just like when we were looking at sample means, we can also build confidence intervals, okay? So we reject here pretty strongly. I think the other example we were using last class, number of births in these oil wells. okay, well, I can come up with these slope coefficients. And we said the way we interpret this, one more oil shale well in a county decreases birth rates by about 3.9 people. However, that test statistic is really close to what? 0. So is that strong evidence that there is an effect? I mean, that would mean that the estimate we found is 0.05 standard deviations below the assumed value of 0. That's not very far, right? And so lo and behold, what is the p-value? 0.96. What level could I reject the null at here? I can't even reject it. Yeah, at any of our conventional levels, could I reject this at the 5% significant confidence level? This is a weird one to think about, but if I had 5%, could say something with 5% confidence, first of all, Jesus, right? But what would get me up to 100? 95 in decimal form. The p-value isn't even below 0.95 here. I can't even say that this is an effect with 5% confidence. This result tells me essentially there's no relationship between these two variables. Okay. So we can start to think about these things from the output that we see, not even close to significant. Now, I also said we can build confidence intervals. So when we're looking at sample means, all the confidence interval is doing is it's saying it's a slightly different way of doing hypothesis testing in a way for two elements. So it's saying based off the sample evidence I found, here are the possible true values for the population statistic. So what I'll do is I'll take my sample mean, I'll go a certain number of standard deviations away that would kind of correspond to whatever level of confidence I want to say. So alpha was kind of corresponding, right? 0.1 would be 90% confidence, but I also have two sides here. So I'm dividing alpha by 2 so that half of alpha is on each side. And then if this is the number of standard deviations away I'm going, well, I need the actual value for the variable. So it's this number of standard deviations times whatever the actual standard deviation is. We can do the same thing for slope coefficients. We're just replacing our sample mean with our slope coefficient. These values will always be the same. It's the ones I wrote down before, right? 1.645, 1.96, 2.58. So what Stata will always tell you, and there's ways to change it, although it's a little bit probably not worth our time to kind of go in through all the settings. We're generally just, going to be 95% should be enough for us. It'll tell us the 95% confidence interval. You can go in and have it give you the 90 and this is just the default. So notice here, based off of the sample evidence I found, what is the range of possible true values for the coefficient between births and oil shale wells? Well, it could be anywhere in between these. It could be negative 100. It could be 75. It could be negative 20. It could be 143. Any value in this range, if we did a hypothesis test for any value in the confidence interval range, well, if these are possible true values, if I did a hypothesis test for them, would I reject or fail to reject? So if I am telling you that every value in this range is a possible true value for the true slope coefficient, well, if I do a hypothesis test, if I reject it, I'm saying that isn't the value. So if these are the possible values, if I do a hypothesis test, I would fail to reject. Every value in that range for your confidence interval, you would fail to reject if you did a hypothesis test. And I should say this to be technically correct, a two-tailed test, right? But that's all we're kind of working with here. Okay. So anything in this range could be possible true value for that slope coefficient. So if I go back, I think I didn't put it here. Yeah, there we go. So we go back to our other example. We had something that was we could reject at every level. So we definitely could reject at the 95% level with a p-value of 0. What are the possible values for the true coefficient here? They range from negative 350 to about negative 150. Notice all of these are negative values, right? And in fact, if I run a hypothesis test for any value in this range, would I reject or fail to reject? These are the possible true values. For any value in this range, I would fail to reject. These are the possible true values. Now, when we run our hypothesis test, what are we always running that hypothesis test against? The assumed true value of. So what are we really looking for with our confidence interval? We're looking to see, does it include 0? If it includes 0, I can't say that 0 isn't the true value because it's in my range. Anytime I have a confidence interval that doesn't include 0, well, these are the values that I can't reject the null for, which means any value outside that range, which now includes 0, I can reject. Any value outside of that confidence interval, if I did a hypothesis test for it, I would reject. So here I can definitely reject 0, right? Because it's way over here if I'm plotting it on a line. Just starting hopefully to, I don't know, kind of come together. We're kind of putting all the pieces together here of things we've talked about in relation to this linear regression. Questions here before we keep moving. Oop. Okay, so we've talked through statistical significance, but just because we have statistical significance doesn't necessarily mean we have economic significance. So we'll start to kind of talk through these ideas when we start to look at different data sets. So, you know, I don't know. If I looked at these results, highly statistically significant, right? We could reject 0 with any level of confidence. Is it economic? Let's assume, like I said, I think if I remember, income might actually be weekly here, but let's assume this is annual income. When we talk about economic significance, just because something is statistically significant, if it doesn't have a very large impact, we might not care about it very much. So if using marijuana one more day a month decreases the amount of money I make by $253 over the year, is that a really large effect? I mean, we could debate it, but not really. We're talking about incomes in the 50, 60, you know, I average around 50,000, something like that. So this is probably not the most economically significant effect, okay? So when we're talking about economic significance, we're generally looking at like the size of that coefficient. If it's relatively small, right, then we may not say it has economic significance. If it's relatively large, it would. Now, there's a little bit of a caveat to that, which I think we'll look at in the do file here in just a second. But in an ideal world, we would find statistical significance and economic significance. And it also goes the other way. Let's say I find something and it has a p-value of 0.2. Well, can I reject at any of my conventional levels? 0.2 be less than 0.1, 0.05? No. So I don't have statistical significance at my like benchmark values. But what level could I say? If it's like, let's say it's 0.19. I could say with 80% confidence, right, an alpha of 0.2 I could reject. So it's not the most statistically significant. But let's say I found that marijuana coefficient was like, I don't know, negative 10,000. Just because I don't have the strongest statistical significance, if the coefficient value is really large, well, that's could be important, right? That has a large economic significance. So what's one thing I could do to get more statistical significance? So if I find something that has a very large coefficient, large economic significance, but it's not quite statistically significant, what's one thing we said always lower my p-value? If I go out and get a larger sample size, right? So if I go out and get a larger sample size, if what I found was like a valid data set, right? And I find another one, but I just have more individuals or more observations in it, then maybe I will have statistical significance. So I don't know, it's kind of a more nuanced discussion. There won't be like as many, I don't know, questions on a quiz, but we'll start thinking about these things as we talk through the data, okay? Now, you know, just because we see large coefficients, that's also not necessarily telling us there is economic significance, right? Or if I find a really small coefficient, that's not really telling me there's necessarily low. Why? Because what actually matters is that change in the variable, is it a large percentage change? So if I had some regression where I had GDP as my Y variable, changes in GDP of like, I don't know, 100,000. Oh, the coefficient's 100,000. That's a large economic significance. Well, what are GDPs? They're in the billions, right? If not trillions for most, so the upper end. So 100,000, is that going to be a large economic significance? No, right? So we have to put it in the context of whatever variable we're looking at. Same kind of idea. If I'm looking at GPA data and I see a change of 0.3, oh, that's pretty small, right? Well, no, GPAs are from 0 to 4, or go a little bit above. 0.3 is a pretty sizable change in something that can only be between 0 and 4. So we want to think about economic significance, not just in kind of the size, but the relative size of that coefficient to the variable itself, okay? And usually what we would do then is how I would compare it to kind of that dependent variables mean, right? To kind of know what, how sizable of an effect is this? What proportion of that y variables mean would this change be? Okay. And then we can convert that to a percentage change if we're looking at proportions. We'll kind of look through some of these examples. So I've got scaling variables that we're going to look at here and talk about its impact. But we want to do a little bit of work in Stata here. So I'm going to open this up. So we'll kind of skip through here. We're going to go down to issues with scale. Okay. So let's say I run this regression. I had that COVID data, number of cases per 1,000 people, and I had household income. So I run this regression. And I get this coefficient of 0.0004. I'm like, it's not that big of a deal, right? Pretty low economic significance. Now, is it statistically significant? Highly. P-value is 0. I can reject at every level here. Well, if I'm looking at household income, what would a change in my X variable be? One more. This is from the US. One more US dollar, right? If my income goes up by $1, what would I expect the size of the effect to be? Relatively low, right? So if on average, a county's average income goes up by 1, I am going to see a relatively small effect. Okay? So I might want to think about, well, what would be a reasonable change in income that would produce an effect? I think we looked at this last class. I can scale that variable by creating a new one, which is just, well, what is the average or median income in that county? And scale it by 1,000. So now every 1 unit change is not $1, but it would be a $1,000 increase. So what should happen to my coefficient? If this is the effect of a $1 increase, when I change the variable and I run this new regression, I should find the exact same value, but what? I'll move this decimal point, right? Instead of a $1 increase, my new variable, every 1 unit increase would be an additional $1,000. So it would be the same coefficient, but move the decimal 3 places, right? So now if I create this new variable, which is the old income divided by 1,000, so I've just changed the units. Now when I run my new regression with this scaled variable, notice I get the exact same coefficient as I had before. It's just that I've moved the decimal 3 places to the right. And so now if I have a $1,000 change in the average income in a county, per 1,000 people, see about 0.4 fewer COVID cases, which once again, we have to think about, is this economically significant? 0.4 might be a low value, but if this was the cases per 1,000 people, I mean, some counties have millions of people. This might be a large number of people, right? So scaling a variable, you always want to think about what the units of your variables are in. It's kind of the result of this story, right? But you can always change those units, right? Because here, if I'm dealing with something like GDP, I don't want to show somebody a coefficient that's 0.000002, right? I might want to scale that up so it's like a little bit more digestible to look at and has a little bit more actual meaning. Like we're not going to see $1 increases in, GDP. I could see $1 million increase and that wouldn't be the craziest thing, right? So it's always going to depend on kind of what 2 variables we're looking at, what makes sense. But this idea that we can scale variables in Stata really easily, we just create new variables, right? And then we can, here I'm scaling it by 1,000. I could do the opposite way as well. So I think here, we didn't talk about standardizing variables last class. I'm going to jump the gun a little bit, but if I run these 2 regressions, so the one had the original income variable, the other had my scaled variable. What should happen to my R squared? So remember last class we were talking about the R squared told me what? So it was the proportion of the variation in my Y variable that what explains. I'm running this regression. What is the only thing I've included in my regression? It's X variable. So our R squared was a measure of what proportion of the variation in this Y variable, which I'm trying to predict. That's the whole point of this linear regression, is I ultimately want to try to predict what that Y value is going to be using this X variable. So it's what proportion of the variation in y is explained by my x variable. If I've just scaled the variable, have I changed this relationship at all to y? No, I've just scaled it. So my r squared, if that's just the proportion I can explain, scaling this x variable should do what? Not change my r squared at all, right? And sure enough, if I look at this, after scaling that variable, my r squared is what? 0.1098. Before, it was 0.1098. So scaling my variable won't change my r squared, but it will change my coefficient estimates. Because the coefficient estimate, the interpretation there was a 1 unit change, and by scaling it, I'm changing the units. But simply by changing the units, I'm not changing kind of how much of x can explain of that y variable. So let's get some other kind of weird regressions down. This might kind of help us answer some questions. And also we might see this kind of pop up in different regressions we look at. So what I'm going to do here is I'm going to go back to that original income variable before I scaled it. I'm going to create the mean of that variable and store it as a new variable. So this isn't that interesting. So we said, when do we use gen or egen? Egen was when I'm using built-in commands. Gen is if I just want to do like a general math or conditional statement. So I'm going to create this new variable, which is mean income, which is just the mean of household income. And then I'm going to create another variable, which is the standard deviation of income, which is just the standard deviation of income. Okay? So when I create these two variables, I can kind of take a look. It should be for every observation, it's always the same, right? The mean income is always the same for every observation, right? I'm looking at the mean across the whole data set and the standard deviation across the whole data set. But what's useful, if I have these in there as different variables, how would I standardize a variable? So I know we talked about this already. So how would I standardize a variable? I take the values for that variable and do what? If I want to create standardized variable for any variable x, I'm going to take the value for x, I'm going to subtract my mean, and I'm going to divide by my standard deviation, or kind of think about my standard deviation. Oh, thank you. Right. So when I standardize this variable, right, we get some kind of interesting things to think about, right? So if I am now looking at y, it would be my intercept coefficient plus my slope coefficient. Usually it would be multiplied by my x variable here. If I run a regression where I've standardized the x variable, the variable I'm actually using is going to be the standardized version. Okay. So for a second, I'll kind of ignore something, and math is a little bit more tricky, but I kind of want to get at this concept. So let's say, well, I don't have to simplify it. You guys can handle this, I think. So if I plug in the equation I had for that standardized version, that's what I've got. Okay. Now I think I had this in a slide from last class. If not, I'll kind of find it and point it out to you where it is in those slides. But if I wanted to find my intercept coefficient estimate, it actually ends up always being my average y minus whatever the estimate I get for that slope coefficient is times the average x value. So that was going to be kind of how we ended up calculating kind of what that slope coefficient was. Or sorry, slope coefficient, what the intercept coefficient was, okay? So notice if I rewrite this, okay, got my kind of average y. If I take the average of x minus the average x divided by that standard deviation, what is the average of x? Well, this would just be my average x. Every single variable, when I subtracted the average, well, if every thing has the average of the average will be So if every single, remember that new variable I created, every observation, it was the same value. So when I take the average of that, it's gonna just be that value or the average. So now I can think about the average standard deviation here, doesn't really matter. Notice, what should my intercept coefficient be from a standardized regression? What is this always gonna be? 0. 0 times anything is 0. So an intercept coefficient, if I standardize my x variable, should simply represent the average y variable, right? Or when the x variable is 0 standard deviations away from the mean, this should be my average. So we'll see if that's true. Well, hopefully the math, I'm not lying to you here, right? So from that regression file, I'm going to create this new standardized income variable where I just take the income, that was my x variable, subtract the mean income, divide by the standard deviation. So I go ahead and do that. Now notice, this will have variation. Because when I standardize a variable, what do these numbers actually represent? So if I standardize a variable, it now represents how many standard deviations away from the mean that observation's value for income was, or for that x variable. So some of them will be below the mean, some of them will be above, right? But we've just kind of created this now so it's the number of standard deviations away. So now if I run a regression, and let's say I'm going to look at this vaccinated variable as my y variable, and I'm doing the standardized variable I created as my x variable. Okay. So let's think about how would I interpret my slope coefficient? So my slope coefficient is going to be a 1 unit change in x. Well, what is my 1 unit change in my x variable now? If I've standardized it, it goes from 0 to 1. That's representing a county that had income that went up by 1 standard deviation, right? So if the income in a county goes up by 1 standard deviation, the predicted change in the percent of that county that gets vaccinated is about just under 5%, right? I think vaccinated was in terms of percentages here, okay? So it's a pretty sizable effect. I mean, 5% more of your population, if it's just a 1 standard deviation. Now, 1 standard deviation increase is going to be a large probably increase in income, but probably some economic significance. Now, is it statistically significant? Yeah, pretty strongly statistically significant. P-value of 0. Now, how would I interpret the constant? We said if I've standardized the x variable, the constant should be the average y variable. So that should be the average percent of a county that's vaccinated in this data set. So hopefully, what's one command I could use to check this? If I just did sum that y variable, hopefully it tells me the mean is 40.77. Fair enough, it's 40.77. Okay. So when we standardize that x variable, that slope coefficient will always now have like some real relevant meaning to us. It's telling us where the mean of that y variable is. Okay. So, just kind of an interesting kind of thing we can kind of link up to things that we've talked about before. So I think if I go back, let me see here, do I have it down here? It's going to be in last week's slides, unfortunately, I think. So I originally had this in last week's slides where before we standardized it, I gave you kind of what that intercept coefficient was, but we can kind of see here, proving it to ourselves with data, that will hold. Okay. All right. So where are we at on time? We got another 20 minutes here. Oh, see, what do I want to do here today? I think maybe another 10 minutes here. So we kind of already talked through some of this economic significance and scaling stuff. Let's now think about the R squared. So I will show you in Stata where it gives you these, but Stata will report to you the explained sum of squares. So essentially you can think about this numerator is what percent or what is the total variation that existed in your y variable that you explain with your x variable. And then TSS is the total sum of squares. That's just the total variation that existed in y. So that's why we could interpret our R squared as the proportion that our x variable can explain relative to the total variation in y that exists. So we sometimes will convert this to a percentage by simply multiplying it by 100, but our R squared that is going to be reported to us from Stata will always be as a proportion. Okay. Now we can do 1 minus this. We're not going to worry about this too much for right now, what these represent, but this is basically, if this is what I can explain, this is what I can't, right? So if this is the proportion I can explain, that's the same as 1 minus the proportion that I can't. So if we actually look at how our adjusted R squared is calculated, so my R squared, and this is going to become a little bit more relevant once we get to multiple linear regression, but let's think about it this way. If I have more observations, do you think it's more or less likely I can explain the variation that exists in a Y variable? If I only have 2 observations, I think it's more or less likely I can explain why a variable is changing as if I had 2 million observations. Probably less likely, right? So our adjusted R squared is going to account for the fact that even if I see the same slope coefficient, or even if I see the same explained sum of squares, it means more if I found it from a larger data set. So our adjusted R squared, which it's R squared with a bar over it, or so I'll usually write it as like ADJ, just to kind of signal like this is the adjusted R squared, is a slightly different calculation, right? So it's going to scale up the proportion that I can't explain. So we can kind of start to think about this. And I'll kind of use some directional changes here, point something out. We'll take a look. This looks like, right? So if I've got my R squared, I'm looking at the adjusted R squared. So I said that is 1 minus the proportion that I can't explain. This would be the same as the proportion that I can explain. Well, if we scale this up, I think it's n minus 1, minus 1 over n minus k. Now, for us right now, k doesn't matter because it's the number of variables we're putting on the right-hand side. We've only used 1 up to this point. So for us right now, k is just 1. Okay? But notice, let's say I had a sample size of, 10. So if this is always 1, if my sample size is 10, what is this fraction? It's going to be 10 minus 1, so 9, over 10 minus 2, so 8. Okay. So 1 minus, and this will be something, we don't know. Let's say it's just 0.2 just to put a value to it. So the proportion we can't explain is 0.2. Right? I then kind of do this math and I get my adjusted R squared. Okay. If I instead had a sample size of 100, okay, even if I found the same proportion that I can't explain, but now what would the numerator and denominator be? What? 100 minus 1 is 99, and this would be 98. You could put this into a calculator, but what is this going to get closer and closer to? 1, right? So this starts out as a higher value. As I get a larger sample size, what's happening to this fraction? It's getting closer and closer to 1, or it's going down. If I'm subtracting a smaller value, what's happening to my adjusted R squared? It would be going up, right? So my adjusted R squared, when I take higher sample sizes, well, I'm still seeing the same proportion that I can't explain, but it's not getting scaled by, it's not getting kind of multiplied by as large of a factor, right? So essentially what this results in is as I take a higher and higher sample size, my adjusted R squared is going to be closer and closer to whatever that original R squared value is. Because I'm essentially just multiplying this by 1, which if this was 1, I have the equation that would just give me my regular R squared. So this is another situation where we have a statistic that's influenced by the sample size. The higher the sample size, right, the higher and higher my adjusted R squared will get, or the closer to my actual R squared will become. Now, if I'm subtracting, what is this fraction always going to be greater than? 0. What is it always going to be greater? N minus 1. If I took n minus 1 over n minus 1, I'd have what? 1. So if I'm always dividing by something that's a little bit smaller, this is always going to be greater than 1. So instead of calculating my r squared, I'm always going to be subtracting something that's a little bit larger. So my r squared will always be larger than my adjusted r squared. As my sample size goes up, that adjusted r squared is going to get closer to the actual r squared, but it'll always just be slightly below it. And, hopefully kind of prove this to you once we start looking at some of the state output that we're already looking at. Okay. Questions? Yeah.
Yeah, sorry if I missed it. What's K?
This is going to be the number of variables that we've included. Up to this point, we've only looked at 1. Starting next class, we'll start adding in more. So we'll kind of actually revisit this later on as well. Okay. So, there we go. So here I've got my adjusted r squared. I wanted to actually go back. Do I have anything here? We kind of just talked through all of this. This is just kind of a summary of what I wrote out, just not arrows and things like that. But I wanted to go back to that output. There we go. So notice my adjusted r squared is always going to be lower than the r squared. Now, it's not much lower here, but why? Because I've got a really large sample size, right? If I had a smaller sample size, that adjusted r squared is going to be quite a bit below. Okay? In fact, here with that shale well, notice, we get a really weird example here. And the reason why is because it wasn't, right? We couldn't reject it. No, we actually ended up with a negative. This is a very bizarre example. But it kind of shows like that gap in between r squared and adjusted r squared with smaller sample sizes can be quite a bit larger. Okay? And I'll try to kind of point this out as we look at more examples here. Okay. So we were just talking about that adjusted r squared. We haven't talked about adding more variables, so we're going to hold off on this till next class. I just want to kind of point out the sample size here. We already looked at that on the side. So the next thing that I want to go through, we've got what, 10 minutes? Ran myself out of time here a little bit. These are interesting examples. But to make sure we had time. Yeah.
The point of our adjusted r squared, like when would we use that instead?
So for right now, think about it as it's accounting for the fact that even if we found a relatively high r squared, if it only was coming from 10 observations, it's going to really penalize that and lower it quite a bit because it's not a very high sample. I might have just happened to get 10 individuals that had this strong relationship with Y. And if I had 1,000, maybe I actually wouldn't see it explain as much. So it's kind of penalizing us, or it's scaling the r squared to account for like, this isn't coming from as many observations.
Sure.
Once we start adding in more variables, it has another role as well, but we haven't started adding in more variables yet. Okay. We looked at a little bit of this dummy variable stuff last class. I think I'm gonna look at quiz for today. We'll kind of end on that. So we'll talk through some of these. I'm gonna give you the answers here. So what? Got one. In the class here. Today's the 23rd, just making sure. Save and publish this. Should pop up on the home page under week 5. So it's this in-class kind of quiz 3, okay? So if we looked at this, I might gloss over things a little bit that we haven't completely talked about, but we have talked about enough of this that I do want to take a look at it, okay? And I think seeing this, like the types of problems you'll see somewhat kind of helps us think a little bit more about what we're going to see once we get closer to that exam. So, okay, got a spinning wheel of death here. There we go. So we didn't quite get to talking about these dummy variables. And so they'll be a little bit weird, but it really shouldn't be a whole lot new. In fact, I'll gloss over these. I'll go through these slides pretty quick because we're just rehashing what we've talked about. It's just a slightly nuanced variable. So let's say I was running a regression with that COVID County data. And instead of a continuous variable, my Y variable is just whether or not it was a metro county. Okay. So how would I interpret my slope coefficient? So if I have the unemployment rate is my X variable, if it's measured in terms of percentages, it would be when the unemployment rate goes up by 1%. Right, so when the unemployment rate goes up by 1% here, right, the predicted value of my Y variable goes down by 0.045. Now, if my Y variable is just a 1 or a 0, 1 if it's a metro county, 0 if not, how can I think about changes in that variable? Well, 1 would mean the probability it's a metro county is 100%. A 0 means the probability it's a metro county is 0%. So when I have a 1, 0 variable as my Y variable, changes in it will be changes in the probability that you see that variable take on a 1 value. So if my unemployment rate goes up by 1%, the change in the probability it's a metro county, right? Because it's just 0 if it's not a metro county, 1 if it is, right? So the changes in whether or not, or changes in the probability it's a metro county would go down by 0.045. So it's still kind of using the same template, a 1 unit change in my X variable. Here, unemployment rate is measured as percentages, so a 1% increase in unemployment rates changes the predicted probability of this Y variable, because my Y variable is now just a 1 or a 0. So now when I have a 1, 0 Y variable, the units of my Y variable are just probability, okay? So the probability would go down by 0.045. So that's going to be kind of our answer for that first one. Any questions on this idea? We'll kind of look at a few more examples with dummy variables next class. Okay. So what if instead I flipped it? And I've got south on my right. So south is just a 1 if it's a county in the south, and I forget exactly what states this included, but right, 1 if it's considered to be in the south, 0 if not, and then the number of new COVID cases. Well, what levels could I reject the null hypothesis that there is no relationship, right? So we always start out assuming there is no relationship. What levels, this is a bit of a tricky one, could I actually reject that null hypothesis at for whether or not the county was in the south here? So what's its p-value?
0.01.
0.01. So can I reject at the 90% level? Well, is 0.01 my p-value less than an alpha of 0.1? Yes. So I can reject. What about the 95% level? Is it less than 0.05? Yep, so I can reject. What about the 99% level? Is it less than 0.01? It's equal to 0.01. In fact, it rounds it to the third decimal. So that means there's value somewhere out here. So it's just slightly above 0.01. So even though it's close, I would actually fail to reject at the 99% level, which means the only levels I can reject, 90 and 95%. Okay. So we still, once we have these dummy variables, treat them the exact same way we did this as a continuous variable. We're just looking at the p-value, comparing it to alpha. So nothing new when it comes to deciding statistical significance. The interpretations get a little bit different here, but our statistical significance, we do the exact same way. Okay. Now, let's think about instead. So actually, we already talked through this one, so hopefully it's easy. But I said, if we standardize a variable, so let's say I've got a simple linear regression, crime rate is my dependent variable. So anytime I give you a dependent variable, that is what is going to depend on something else. That's what's on my left-hand side or my Y variable. So if I was writing this out, it would be crime rate is equal to intercept coefficient plus my slope coefficient times my independent variable, right? Or the thing that is changing on its own, which was unemployment rate here. If I'm thinking about my intercept coefficient, if I standardize that X variable, or I standardize that independent variable of unemployment rate, we said the intercept coefficient should tell me what? So when I standardized that X variable, the intercept coefficient was just the mean of my Y variable, right? We kind of did I've got it right here. We said that intercept coefficient was just the mean of my Y variable. So here, if I had this regression, what would the intercept coefficient be equal to? The mean of my Y for my dependent variable. So it should be equal to the mean crime rate. Right? So there, we should have it kind of being equal to the mean Y variable, which was our dependent variable, so the mean crime rate. Okay? So these are something we kind of already talked about here today. So to use the remainder of our time, thinking about question 3, this one is a little bit tricky. So we've got all these things and we have a smaller sample size. So I think I did a lot of stuff with larger sample size. So let's think about the opposite, right? So let's say I have a smaller sample size. Which of the following things are going to change? Okay. In fact, let me move this here so I can make sure I'm getting these right. There we go. You guys can still, okay, perfect. So we had the p-value associated with our test statistic. Okay. So this is actually kind of going back a little bit. But if I have my standard error, right? We said this was equal to kind of the sum, kind of my errors here, divided by n-2. So I've got like the sum of my errors. So we're only focusing on kind of my sample size here. So we then think about my test statistic. We said, well, we'll take that slope coefficient, divide it by the standard error. We're subtracting 0 technically. And then when we thought about our kind of R squared, that was going to be 1 minus the proportion that we can't explain. And our adjusted R squared was 1 minus that proportion we can't explain, but scaled by n-1 over n-k-1. So if my sample size is smaller, what's going to happen to my standard deviation for my slope coefficient? My denominator is smaller, that standard error is going to go up. So my standard error should change. Okay, so that'll be influenced by my sample size. Well, if my standard error changes, what's going to happen to my test statistic? It's going to go down. It's going to change as well. Okay? So my standard error, my test statistic will be impacted by my sample size. If I was thinking about, if I had a test statistic and I was finding the area to the right, multiplying it by 2 to calculate my p-value, if my sample size goes down, my test statistic is going to go down. What's happening to my p-value? Well, that area is going to be larger, so my p-value is going to go up. That area represents half of my p-value, so if it's larger, my p-value will be higher. Okay? So my sample size going down influenced my standard error, my test statistic, and my p-value associated with that variable. What's going to happen to just my R squared? Nothing at all, right? What's going to happen to my adjusted R squared? Well, we said if my sample size goes down, I can always put hypothetical values. I'm going from like 100 over 99 to, I don't know, 3 over 2. This value is becoming larger, which means if I subtract a larger value, my adjusted R squared is going to be smaller. Our adjusted R squared was also influenced by our sample size. So here, kind of thinking about which of these, I have to change the date. Here, let me do something we submitted. So I think we had here, the p-value will change, the standard error will change, my adjusted R squared will change, but these other two won't. So the R squared and the test statistics should remain exactly the same. Or sorry, no, I said this wrong. P-value, standard, all of these in fact will change except for which one? R squared. Yep. Okay. Questions? Make sure you're kind of getting that submitted here. I'll change the due date so it's switching over. Yeah.
Oh, and this just says the test statistic on the south.
Don't worry about that one. I didn't actually, I know what I meant to do. I'll tell you here in just a second. So I'll update this also so that like no one was treated late because I know that we kind of got pretty close to it. I didn't actually want that to be test statistic. Now that I'm looking at it, I actually wanted it to be the coefficient. So the coefficient you see will not be impacted by your sample size, right? So the R squared and the coefficient that you see won't be impacted. Every other thing that we talked about will be impacted by that. So I'll get the change. I'm going to regrade it here. as soon as you guys are done. I'll get those sample questions 3 popped up. We'll very quickly do dummy variable stuff since we kind of already touched on it here at the end. I'm gonna probably switch over to looking at multiple linear regression, thinking about the types of things you'll see on the next problem set next class, okay? Any other questions for me? Hang around for a little bit. Otherwise, I will see you guys on Thursday.
Thank you.
Thank you.